It is now started happening. Yes. So do you have any question or comment regarding our last class? So okay. If okay, so let's recap that what we learned in our last class. So far we learned the contiguous memory allocations, and in last class actually we start some basic. I just gave you some basic idea regarding the paging or non-contiguous memory allocation. Today actually start from here that what is the paging things and how it works. And of course, this is the non-contiguous memory allocations. As you know that for contiguous memory allocation, there is two things. One is for fixed partitioning, and another is variable partitioning. And you know that there is kind of major problems like in fixed partitioning, it suffer by the internal fragmentation, and for variable partitioning, if you use a variable partitioning for contiguous memory allocation, it may also suffer by the external fragmentation problem. But if we use the non-contiguous memory allocations, we can actually read off the external fragmentation problems. Also, in our last class, we also saw that one thing you can do for compaction. But in compaction, problem is that that it takes time. Also, CPU need to execute another process or function from your operating system. Is every time interval your CPU need to execute another process from your operating systems to actually fulfill the compactation process. In compactation, what it does, every time intervals, your all process copies together and all holes actually created together. So this is how you can also read off the external fragmentation problem. But problem is that it takes time, also time consuming, also need to execute process every time intervals. And next option was that we can use the paging technique. If we use the paging technique, then we can solve also the external. We can solve the external fragmentation problem as well. So let's explore what is the paging techniques. Today we'll explore in details. Okay, before I start, let me share my screen from my iPad so that we can draw some pictures. So if you have any question or comment, please ask me. No worries. Okay. Turn off my video first, and then it will be easy to more smooth. Let me share my screen. Okay. Okay. Let's see what is actually paging. Paging means actually how paging technique works. Let's explore these things. Let me draw figures. Your memory or RAM. This is your RAM or your memory, and okay, this is your RAM, and let's say this is your one process. Let's say this is P1, and I'll give the name. This is RAM, random access memory, or your or in short, we can say this is RAM. How paging techniques works? At first, your RAM is divided into some fixed partition. Fixed partition means the fixed frame. Here it says this fixed frame. Your RAM is divided some fixed frame. Some frame. Yeah. And also your process also divided into some partition. It is called page. Some partition. Your process is nothing but space. It can be 10 MB, 10 MB or 10 KB or whatever it is. This also divided into some we can now we can say some partition, and each partition is called the page. Your process is divided into some partition. This partition is called the page, and your RAM or memory is also divided some partition. It is called the frame. Here is two things: frame, and another thing is page. Page. There is two things: page and frame. The partition in RAM is known as frame. The partition in your process is known as the page. And frame size is equal to page size. Page size. So from here you can understand that what you can do, your operating system can do. Your operating system actually can actually insert one page inside a one frame, and this page can be also inserted, let's say, in here. This page can be inserted in here because frame size is equal to page size. Okay, so your operating system can actually insert or can allocate the memory for each frame, each page for each frame. So this is the one of the basic base concept for paging techniques. And now we can say that what would be the page, actually frame size and page size in actually modern computer systems. Usually most of the cases it is 4 KB. 4 KB they manage in 4 KB for page, as well as the frame size is 4 KB. This is the standard page and also frame size. Okay. Now let's see how actually how your CPU execute the process from your by using paging techniques. These things we need to learn. Before I jump into execution technique, let me actually give you one example. We would like to explore by using one example. Let me clear this page, and our, let's say, for experiment, for actually example purposes, we'll consider our process size. You open a process, its size is 16 byte. It is usually a large size, but for example purposes, we use the 16 byte so that we can easily understand that how paging works. Okay, and let's say your RAM size or memory size, let's say 64 bytes. Actually, it's nowadays it is GB days. Just for an example, we consider these things. And as you know that our page size always in the page size is equal to your page size equal your frame size. Always we know. Frame is the partition for in your RAM, and page is partition in your process. And we consider this is 4 bytes. This is 4 bytes for each frame size as well as your RAM size. So now we can think about this. How many actually, if frame size is 4 bytes, so how many frame will be inside the 16 MB 16 byte RAM? This is process size is 6 byte. So 64 divided by 4. So total frame will be 16 frame total. Total 16 frame. 64 divided by 4. Okay. Total 16 frame. This is 1, 2, 3, 4, 5, 6, 7, 8. Let's say 9, 10, 11, 12, 13, 14, 15. Let's say this is 16. Total 16 frame. All are same. All size is 4 bytes. 4 bytes. 4 bytes. All are 4 bytes. They are all are 4 bytes. It is start from 0, 1, 2, 3 physical address till 15. It start from 15 to total 16. So this is your RAM configuration for 64-bit RAM if the frame size is 4 byte. Also, our assumption is our process size is 16 byte. 16 byte. Also, you know that process frame size is equal to the page size. So, what is the page? How many page will be this process for 16 byte? If it is 4 byte, each page size is 4 byte. So total, it will be total 4 pages will be there. Each page is 4 bytes, 4 bytes, 4 bytes. As you consider our process size is 16 byte. So there will in your process, how many page will be there? Page will be total 4 pages. Let's say this is process P1, this is page P0, P1, P2, P3. Can you understand this? Do you have any question or comments? Okay. Here is main actually assumption is that main consideration is that your page size is equal to your frame size, whatever it is. When you use the paging technique in operating system to execute the process, your page size should be equal to the frame size. Depending on your page size, your process is divided into some partitions. Also, your RAM is also divided into some partitions. Depending on the frame size, RAM will be divided, or page size. This is same thing. Also, depending on page size, it's also your process also divided into some parts. Now let's say our process, this is our process looks like. So each process, how many so each process contains total so each page contains total 4 bytes. So each page contains total 4 bytes. 4 bytes. Each page contains total 4 bytes. So your total 16 for your 16-bit process. For your 16-bit process, each page contains total 4 bytes. Now let's consider one more thing is that this is let's say this is a byte addressable system. We already know what is the byte addressable system. Let's say this is, for example, this is byte addressable memory system. Byte addressable system means that every bytes in your memory, in your process, or in your memory has its unique address. Every bytes. Here is 4 bytes. So this is your 16 16-bit 16 byte process. So each byte you want to make if it is byte addressable system, so each 16 byte requires 16 unique address. 16 address. Another is word addressable system. In that case, each word in your process has its unique address. Let's say this is byte addressable system for simplicity. So 16 byte require total 16 addresses. So how we can decide how many actually bits is required to addressing 16 for addressing the 16 address. 16 address is nothing but 2 to the power 4 equals 16. So we need 2 power. This is we need total 4 bits. So for addressing all 16 bytes, it is start from 000000001 and also 1111 like this. So now each byte we just we just have its own address. So this space contains 4 bytes. So this is 0 number byte, this is 1 number byte, this is 2, and this is 3 number bytes. So this is total 4 bytes, and each byte has its own address, own unique address. It is a 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1. This is total 4 bytes. Also here also byte number 4, 5, 6, 7, and so on. Here is 6, 15. That is 15, and so on. So this is how it's addressed. This is the address for your process, each byte of your process. So now let's see how CPU executes a process. Before actually start the execution process, one thing I would like to mention in here. So when you create a new process, in your from your disk, you want to execute a new program, or you want to open a new software. What actually your operating system does when you open a new process or new program or new software? Here is two. You are now currently you are trying to open the two programs. Let's say MS Word as well as the Google Chrome or Photoshop. MS Word and Photoshop. So your operating system maintain. I already actually mentioned in this thing in our last class. Your operating system maintain two process table for these two process. Your operating system, when you open a new program or new process, your operating system will create a new page table for this process. This process is create a new page table like this. Here we consider this is your page table. This is your page table. This page table, if this is for page table for process 1, let's say MS Word. If you open another program, let's say Photoshop, also there will be another also page table your operating system actually needs to maintain. Okay, so this is for this page table is for actually it should be unique for each and every processor. Each process needs an page table. So now let's see your page P0. Oh, okay, this is your current memory structure. Let's say this is already occupied by other process. This is also occupied some other processes, and here also some occupied some other processes. This is also occupied in this position. This is currently look like. So your operating system now needs to allocate this process inside the RAM. So how it does? It's actually for this process P1. It's process P1. Sorry, it's kind of weird. This is called, let's say this is for this process table for process table for process P1. Okay, process table for P1. So each page it's just allocated inside the memory. So your operating system keeps searching from the beginning, and it will find a hole in here. So P0, let's say, allocated in this location. And then P1 here, P1 is allocated in this location, and then again P2 is in here, and P3 is in here. P3 is in here. So you know, this is a single process. Also, you divide it into it is a single process. You divide it into some pages. Oh, sorry, this is process. Process. This is not process table. This is process. My mistake. This is process. At first, this is for this one process, and this process you divided your operating system divided into some pages depending on the size, process size, and also page size. And then this process actually inserted inside your memory or RAM, but you see this this page is in different location. It is not in a contiguous locations. Huh? So this is from here. It is understandable. This is an non-contiguous memory allocation. Huh? This is non-contiguous memory allocation. Huh? You have a single this is single process, but you divide it into some pages, and each pages has been allocated in different location inside your RAM. So this is a example of non-contiguous memory allocations. This is 4, 5, 6. This is 6, 7, 8, 9, 10, 11. That's this way. Now, how your CPU actually CPU knows that process P0 actually page P0 is in this location and P4 is in this location and P6 P2 in this location and P3 is in this location. How it knows? So this is a process. So when you open a process, CPU your operating system allocates the memory for this process, and so also by this time your operating system maintain a process table for this process P1. This is called process table. Now comes into the process table, actually how it works. Let's see how it works. This is another thing is called the process table. So let me clear some spaces in here. Okay. So let's see what's actually process table contents. Huh? This is a process table for process P1 for process P1. So what is the entry for this process table? The process table contains the page number P0. There is if it is a process table, so there should be some rows, some entries. We can say this is some rows or entries. So how many entry will be this process table? So it depends on that how many pages in inside your process. How many pages inside the process? Here is total 4 pages. So your process table also contain 4 entry. If it is 10 pages, 10 page, then your process table also contain 10 entry. Now let's see what is the entry will be here. Here is process page number P2 and here is P3. Let me little bit. Here is P3. Total 4 entries. So this process table, and then next P0 contains the actually base address, the location of the frame address. This is F, let's say frame 0, frame 1, frame 2. You see frame 2, we can say this frame address. You see the P0 inside this frame address 2. So it will contain here frame 2. Physical location of page P0. Also F4 for P1, and F6 frame location 6 for P2 is in frame location 6 and P3 is frame location 8. It contains the physical memory address, for the page, for this particular page locations. Do you have any confusion or any questions and comments? Okay. So next from here, what we can what we understood that is page table. Each process has its own page table, and this page table entry is equal to the number of pages inside the process, and this page table contains the frame location, page location in your memory or RAM, for your memory or RAM, computer memory or RAM. Okay. And next, this is the process table. This process table should be inside, somewhere inside your RAM, somewhere inside your RAM, so that your CPU can actually execute. CPU can gets this process table, gets the data from this process table, and also executes the process. So why actually we need this, manage this process table? If it is contiguous memory allocations, contiguous memory allocation is your CPU maintain one thing only. Your CPU maintain only a base address, and after this base address, if it gets this base address, and then it is also increment one by one and execute the process, whole process. But for this non-contiguous memory allocation, actually it is not like a CPU execute the process for P0. It's get the starting address for P0. It's get the starting process for P0 page, and then execute the P0, and then also adding some data. There is another process. It should be maintained. This is and every location, every page location for each pages. That's why you need to maintain the page table for every process. Okay, so this page table should be one of inside one of your page frame. Let's say it is inside, this is PT for page table for P1. Here is inside, it's located in that location, this page table. Okay, so now you can say that what would be the size? You know this already. The size of page size as well as the frame size is 4 bytes. You already know this. So you can say that what would be the size for this process table? What is the size for this page table? What is the size for this page table? Now this size actually depends on how many pages in your process, and also the size of your RAM. This size depends on two things: the number of pages inside the process, number of pages inside the process, as well as the size of your RAM. How actually it's addressed for each frame. Here is total 16. For our simplicity, consider the total 16. Total 16 frame. Total 16 frame for 64 byte. So to address this total 16 physical locations, we need how many bits? We need 4 bits. You know already this. We need total 4 bits for 16 for addressing the 16 items or 16 locations. We need total 4 bits. So each address is F2, F4, F6, F8 is total. If you convert it to the binary, let's say it's converted to binary, means that F2 is nothing but 0, 0, 1, 0, and here F6 is 4. So 0, 0, I think 1, 0, 0 is kind of like this, and 8 is 0, 0, 1, 1. This is 7. 8 is I think 1, 0, 0. End up like this. Total 4 bits. Total 4 bits. Exactly total 4 bits. So now we consider we have total 4 pages. Total 4 pages. And each page, each address contains total 4 bits to total 16 bits. Total 16 bits for this process size. Total 16 bits, not bytes. Total 16 bits. So 16 bits equal 2 bytes. 16 divided by 8, you know that 8 bit equal 1 byte. So total 2 bytes. Total 2 bytes. This page table size. Okay. Total 2 bytes for this page table size. Now you actually actually allocates your operating system allocates the memory for this page table inside a frame, but this frame size is 4 bytes. You already know this. We consider this is 4 bytes. This is 4 bytes. Your page table size is, from here we calculate that in that case your page size is 2 bytes. Your page your page table is 2 bytes. So here 2 bytes is already allocated for this page table, and in this frame 2 bytes is unused. So can we use this? Can we use these 2 bytes for another process, sorry, another page, or for another page table? Can we use this? This is inside a single frame. Single frame is 4 bytes, but here is process table is page table is 2 bytes. 2 bytes. So our 2 bytes here is going to be wasted. So can we add use this unused space for another page or another page table or process table? Answer is no, we cannot do this. So from here you can also see that there is kind of internal fragmentation problems, or if we actually insert a page table inside a frame, if it is actually if it is size less than your frame size, there still could be possible for internal fragmentation, but it is very small. It is not like as a fixed partitioning internal fragmentation problems. It is very small. Also, another thing is that from here, as we are talking about the internal fragmentation, another thing we can also consider in here, that is there any possibility to internal fragmentation for the paging things when you create these 3 pages? Is it possible to make is it possible to create some internal fragmentation inside the process, inside your page, inside any page of your process? Yeah, here also still there is a chance for internal fragmentation. Let's say now we consider our process size is 16 byte. Let's say if it is 15 bytes process, let's say it is 15 bytes process. So this time your every page size is, every frame size is, page size and frame size is 4 bytes. So here is 4 bytes, 4 bytes. Here you see, here is 4 bytes. P0 is 4 bytes, it's fine. And P1 is also 4 bytes. Here is P2 is 4 bytes. So total 12 bytes, but your process is 15 bytes. So here P3 will be 3 bytes. 3 bytes if you consider the 15 byte process. So in last page of your process may suffer by the internal fragmentation problems, but still it is not as severe as your fixed partitioning systems. It is very small. Okay. So these are the 2 things you need to know about this. And okay, and next we are already in page table in here. We loaded the page table for P1 inside a frame, and from here, when CPU actually execute a process, how CPU will execute a process? Like the process table, previously for contiguous memory allocations. For contiguous memory allocations, you hear about the process table base address. Means that every process, when you create a process for a contiguous memory allocation, when you create a new process, there is one entry for process name as well as the process name and process base address. So when CPU execute the process, it's search from this process table and collect the base address from the process table, corresponding process table, and load it to the base address. And from this base address, it's actually starting to execute the process. But in here, similar as for process table, CPU, it has one in its CPU, in its computer memory, computer CPU, it has one called the page table base register. If it is, this is your CPU, this is your CPU, it has a page table, let's say this is page table base address. This is one register that contain like a process table base register, that is page table base register. This table base register. What it does, it actually contain this. This is 11, 12. This is 13. So this 13 will be loaded inside this base register. Will be loaded inside this base register. Okay, it will be loaded inside this base register. Similar as this process table, this location is always fixed. This location is always fixed. So CPU can, when execute, CPU actually execute the process, CPU searches this fixed location and load the base page table base address inside the register. This is always fixed. So otherwise CPU cannot track where is the process table, location for this process table. Sorry, page table. Here is page table. Where is the location for this page table? So page table is always loaded in a fixed location. It is usually inside your operating system process, inside your OS process. Let's say your OS is loaded in here. So it is always inside your OS process. So it is a secure location. It is always in actually loaded inside a secure location. And from here, your CPU get the base address and it is loaded in here. And what is the next step? And then your CPU is always actually asks for only for this logical address. It at first it doesn't know this physical address. When it gets the base address, when it actually gets the base address in here, it generates the logical address. Let's say it's trying to execute the byte, execute the page 0. Third byte. Third byte means fourth, 0, 1, 2, 3, 4. Fourth byte means if it is start from 0, then it is let's say third byte. Third byte of your process P1. CPU wants to execute this. Let's say second byte. 0, 1, 2 bytes. Second byte from your process P1. CPU try to execute this process. Executes the process P1, and it's trying to fetch the data from second byte. Let's say this is second byte. It's try to execute for the process P1. So what it does, CPU doesn't know anything, so it will generate the page. So as you know, this address is 4 bytes. Also here every address is also 4 bytes. Sorry, 4 bits address. So here it will generate the 4 bits. So CPU will generate the 4 bits logical address. CPU will generate the 4 bits logical address always. It should be like this. Here I don't have space, so let me clear some in here. We know about this. This is byte addressable memory. We know contiguous memory. We know about this. Okay. Yeah. Okay. And this is okay. This is 4 bytes. You already know that this is 4 bytes. And now your CPU is trying to execute the second byte of process P1. So it will generate the 4-bit address. So your address is 4 bytes. Also your process address is 4 bytes. So how actually generate the 4 bytes for this? So first 2 bits, and it is second byte. It wants to generate execute. So it is 0, 1. It generates this type of logical address. Wants to execute the second byte. He doesn't know the physical address or anything. So it is 4-byte address, so it generates a logical address that I want to execute process once second bytes. Sorry, second bytes. I want to get this data. CPU set the command is like this way. So from here, how actually you can interpret this address, this bits address. So here is 4 bits. 4 bits. Here is in your process. You know that in your process process there is total 4 pages. There is total 4 pages, and each process contains 4 bytes. 4 bytes. Yeah, each process contains 4 bytes. Also, there is total 4 pages. Total 4 pages. One. There is let me draw it in here. This is one process page, one second page, third page, fourth page. There is total 4 pages. So first 2 bit. So for addressing the 4 pages, you need how many bits? You need 2 bits. 2 bits will be addressed for this page, addressing the page number. These 2 bits will be for page number. This MSB bit, most significant bit for page number, and then next 2 bits actually represents this which bytes actually CPU actually request for this particular page number, or we can say this is called the page offset. This for these 2 bits for indicates the page number, that which page, and next 2 bits actually represent the which inside in this page actually which bytes CPU are currently requesting for. Also, this is known as the page offset. Okay. Okay. Any question or comments? Okay. So let's move forward. Okay. So you know that this is bits, 2 bits for page number, and this is 2 bits for the page offset or the byte number that CPU is now currently request for your OS operating system. So now how it's interpreted interpreted by your page in your process tables. So this it will now also CPU knows that your process table is located at your page table is located at memory location 13. So it will go to the 13th in here, 13 number locations, and then it will search the in 13 number location what is there. It is inside there is nothing but this page table. This page table, you know, this page table is in here. This page table, this page table is in here. So from this page base register, CPU will actually go these locations, and then it requesting for this. There is a one instruction is like this. It's trying to execute this instruction, and from here 2 bits for allocated for this page number. So it searches the 0 number page. So in this it will be in this locations now, currently 13 location, and then it will keep searching in page table and figure out the where is the 0 number page, and it's find this 0 number page in here. Okay, it's fine. And then it will and then from this 0 number page, it's find in here, and then it will find what is its address. From the 0 number page, it will find the frame number. It is for frame number because P0 is located at the frame number 2 in here. This is in here. So from here, CPU will find this frame location, P0's location. what it does, in here, CPU, you have now 2 bits from these 2 bits. From these 2 bits, CPU identify the page table number, page number, and from here, it's also identify the location of this page number, location of this page number inside your RAM. So it just replace this first 2 bit by using this number. It's 0, 0. These 2 bits is replaced by using your frame number, frame numbers that actually store inside your page table. So these 2 bits is replaced by these 2, but your offset number is same, because your frame size is equal to your page size. Your page size and frame size is equal same, but this 2 bits offset is same, should be always same, but this P0, P0's page P0's frame location or physical locations will actually replaced by these 2 bits will be replaced by this frame address. So now it will be look like this. It will look like this. This is for this frame address. This is frame location for this process P0, for processor page P0, and this is the offset. So here it is nothing but you convert the this is the logical address. Here it is logical address. And from this logical address, you replaced first 2 bits by the frame number. Now it is nothing but physical address. That is nothing but physical address. Now it is actually easy for your CPU to execute the process. It's get the physical address, then this is a physical address, and it will actually it will go in these locations, and then this is that 2, frame number 2, and its offset is 1, 0. It's try to, from here it's try to execute the second byte. So here is 0th byte for P0, here is 1 byte, here is second byte, or if it is 0, this is third byte, or for simplicity you can say this is second byte. Let me erase it and then again this is, we are in here. This is for P0's address, and here is 0th byte. This is first byte, this is second byte, this is third byte, total 4 bytes. So each byte has its own address. So now CPU is in these locations. It gets this frame number from this process, from this page table. It gets the so it will be in here. And then what is the offset? Offset is 0, 1, 2. It will face CPU will face this 2 number, byte number 2, and copy it inside the register. Inside CPU is another register, and from here CPU will execute your process. So it is very, now it looks very messy. So do you have any question or comments? Okay, it is little bit actually little bit complex, I can say, but if you understand this every step by step, it is easy. So what? Let me summarize these things again. So when you create a new process, a process is divided into some pages, and when you also it will be OS will generate a page table for against every process. Against every process, it will generate a page table. What is the page table entry? Page table entry is nothing but it actually look at the physical address for every pages where actually it's loaded. Where it's loaded, or frame number for each pages where it's loaded. Then when also this page table should be inside your memory, or inside your inside your computer memory. So and then from here actually CPU gets the base address, page table base address, page table base address, and figure out the which page it is now actually trying to execute. And from here, this page number will be replaced by the frame number. Then it will be the physical address. Then CPU will move to the physical address, and from this physical address, it will fetch the actually required byte by using the page offset. Here is it page offset for logical address or for paging things. But when the page offset is considered in here, it is called the frame offset. This same thing, frame offset, because page size is same as the frame size. This is also here, it is called the frame offset. Is frame offset. Okay. Okay, this is the summary of paging and how it executes. And okay, so let's see one more items. Okay, in here, so this is the paging techniques actually works. Now one more thing is that I'll just mention in here one more things today. To actually just give one idea is in here. So now you can see that here the page table size actually we calculate this page table size is 2 bytes. 2 bytes. So it is easy to fit in one 4 bytes frame space. You can easily fit it for 4 bytes. Every frame is 4 bytes. You know, we calculate this process. This process. Sorry, this page table size is 16 bits or 2 bytes. 2 bytes. So we can easily actually allocate the memory or insert this memory in a single frame. Let's say we allocate this 2 byte in here, and 2 bytes is wasted. 2 bytes is wasted. This bytes is wasted because this page table needs only 2 bytes. This page table needs 2 bytes. Yeah. I'm talking about this page table. This page table in here. This page table needs 2 bytes. If you allocate 2 bytes is wasted. 2 bytes in here is wasted. So there is a small fragmentation problems. Internal fragmentation problems. But let's think about opposite way, opposite things. If here is frame size is 4 bytes. So you can easily actually accommodate this space inside a one frame, single frame. But if your entry, let's say here is total 4 entry, let's say your process size is, if it is 32 bytes, then it is fine. It will be the 4 bytes, your page table size. Let's see, if it is 36 byte process, then your entry will be the more 4 bytes till the 36. So total it would be 9 entry. Total it will be the 9 entry. 36 divided by 4 bytes, it will be 9. Total 9. Total 9 entry will be here. So then your process table size will be 4 point something. 4 point some bytes. Or let's say for simplicity it requires 5 bytes. Your process tables requires 5 bytes. 5 bytes. So in that case, can you allocate your process? I made all a mistake. This is not process table. Actually, this is page table. This is page table. So this page table now it needs the 5 bytes. So can you accommodate this 5 byte inside a 4 bytes frame? Answer is no. You cannot do this. You can actually here accommodate at best 4 bytes. 4 bytes in here, and 1 bytes you cannot accommodate. So you need to accommodate this 1 byte in another location, 1 byte in another location for 4 byte. That time 3 bytes will be wasted. 1 byte will be 1 frame. So in that case, when you actually for a single, when you accommodate it in a single, when you accommodate it in a single frame, then your actually CPU executor process get by using this logical table based register, it starts from execution, and then it's increment 1 by 1, and actually it's execute the whole process. But your paste table is in different location, 2 different location. So it is not your CPU cannot actually load at only one actually address from these two base table. Actually, it is not able to see, your CPU was not able to actually execute the processor. If it is if your paste table is divided into 2 parts, then you need to consider the multi-level paging technique. Multi-level paging technique. Okay, so today I just give you one little bit idea that when you need this multi-level paging techniques. If your process table size, if your paste table size is greater than your frame size, then you need to go for the multi-level paging technique. You cannot actually manage by using the single level paging technique. That we actually already discussed. This is single level paging techniques. If it is 2 bytes, then you can accommodate in a single page frame, and then your CPU executes your whole process by incrementing after getting the base table base register address, and then it's incrementing 1 by 1 and execute the whole process. But now your base table is in 2 different locations. Your CPU cannot actually execute your process by using only single base table address. So it needs actually another level of paging. It's called the multi-level paging technique. Actually, it depends on your process size. It may not always be used, but when your process size is large, then your operating system always make it for multi-level paging techniques. Your operating system will handle this. And okay, in our next class, we'll see that we'll explore what is multi-level paging and how it works. Okay. So before we go, do you have any question or comments? Okay, thank you. See you next. Okay, we already okay. This will be already done. Next Tuesday. Have a good go to weekend, and see you next Tuesday. Have a good evening. Bye.